So now we're going to enter a series of two presentations on properties of the Laplace transform, and we'll do some examples to show how we can use these properties to find new Laplace transforms. So we'd like to be able to understand properties of the Laplace transform and use those transform properties to find new Laplace transforms. And a little bit of notation, and remember we're going to use this L with a double arrow to indicate that x of t has the Laplace transform x of s, and we're going to call the ROC script r here. Or we might use this L of x of t is equal to x of s, because that notation might be more useful sometimes. Okay, so the Laplace transform is first off we should say the Laplace transform is linear. So remember, we define the Laplace transform as this formula here. And we've already seen, in fact, that it's linear. We saw this when we looked at linear combinations of complex exponentials. But here we can sort of write it down, more formally. So if little x1 of t transforms to x1 of s, and little x2 of t transforms to x2 of s, with ROCs r1 and r2, then for any scalars a1 and a2, if I take the linear combination of the little x's, I get the linear combination of the Laplace transforms. And remember, the ROC contains the intersection of the two regions of convergence, and in general is equal to it unless you have this magical pole zero cancellation. Okay, so let's look at another type of transformation we can do on a signal, and that's a delay. So what if I take x of t and I delay it by t0? So here I'm taking, this is a delayed version of x. Right, so we plug it into the formula here. And then since we're integrating from minus infinity to infinity, we can do a change of variables and say tau is equal to t minus t0. And we're still integrating from minus infinity to infinity. But here we get e to the minus s tau plus t0, so we can factor out this e to the s t0. And we can get e to the minus s t0 x of s. And the ROC remains the same because we haven't changed anything about what s's we need to converge. So the ROC is the same as the ROC of x of s. So since we have this Laplace transform paired delta of t goes to 1, we could see before that delta of t minus t0 is e to the minus st0. And we saw that before, but here, now we can sort of interpret this as this is the LTI system impulse response that delays the input by t0. And it's useful to be able to sort of connect what does the impulse response look like for a given operation that we can describe in words. In this case, we're describing the delay operation. So a system that delays by t0 has a Laplace transform e to the minus st0. So let's do a little example. So let's look at x of t is equal to 3 cosine 4 pi t u of t plus e to the minus 3t u of t minus 3. So here we can see there's a delay. And here we can see there's a cosine. Okay, so we need to use, and here we use the sum, so we need to use linearity. So we're going to use linearity to first do the transform of the cosine part, and so we can pull the 3 out here, and then we're taking the cosine of 4 pi t over u of t, and what is that equal to? Well, we did the Laplace transform of cosine, and it's going to be s over s squared plus 4 pi squared. So the 3 comes down, and we get a 3s in the numerator. And now what about this term over here with the delay? We have to take the Laplace transform of this term. So here I'm doing a little trick. I want to get the t up here to look like t minus 3 because I have a u of t minus 3. So I want these two things to look like 2 minus 3. But what am I doing then? I need to factor out an e to the minus 9, because essentially what I'm doing is I'm multiplying by e to the 9 to get this e to the minus 3 e to the 9 in here. So I get my e to the 9 is going to come outside, and then I'm going to get my delay. So this is e to the minus st0. t0 is equal to 3. And I'm going to get 1 over s plus 3, which is the Laplace transform of e to the minus 3t u of t. right? So this thing delayed by 3 gives me this Laplace transform here. Okay, so what about now? Remember, I can't just have the formula. I need to define the region of convergence for you. So for the cosine, we have the region of convergence was the real part bigger than 0. And then for the decaying exponential, it's the real part bigger than -3. But the intersection of these two is just the real part bigger than 0. So this is the region of convergence for this Laplace transform. So what about a shift of s instead of a shift in time? Well, as an exercise for you, you can go through using the same type of argument as you did in time shifts, and you're going to get that if you multiply by e to the s0t x of t, you're going to essentially shift the ROC by s0. So if you S0 is positive, that is, you're multiplying by a increasing exponential, it's going to shift to the right, which means you're pushing it closer, you're pushing the right half plane for a right-sided signal, you're pushing it farther to the right. And if it's s is less than 0, it shifts to the left. That's a decaying exponential, right? So these are the two different cases. So how can we use this property? So let's do an example. We'll find the Laplace transform of e to the minus at sine omega naught t u of t. And so here we can see, here is our decaying exponential. Decaying exponential, and it's, so we have s0 is equal to minus a. Well, okay, so now if you did one of the exercises from the previous slides, you did try it yourself, you would see that the transform of sine of omega naught t u of t is omega naught over sine s squared plus omega naught squared. And so when I multiply by e to the minus at, I'm going to shift this. So we're going to shift this x of s. I'm going to shift this x of s by minus a. And we're going to shift it to the left by a. And we're going to have then s plus a squared down here, and suddenly what we can see is instead of the poles being at the so the question is, where are the poles? Right, before they were on the imaginary axis, but now you've shifted them to the left, away from the imaginary axis. Continuing with things we can do to signals and then figure out what happens to the transform. We can, of course, speed up or slow down a signal by, say, multiplying by a factor a inside in the time variable. So if you do this, then you plug it into the definition, then you can again do a change of variables, and you'll get essentially that by multiplying by a in the time domain, you divide by a in the s domain, and you get a 1 over absolute value of a coming on the outside here to scale down the or up, depending on if a is less than or bigger than 1, the magnitude of the Laplace transform. So the ROC essentially gets squished or stretched. So if alpha is less than 1, we're slowing down x of t, and the ROC shrinks by a factor of a. And if a is greater than 1, we're speeding up x of t, and the ROC expands by a factor of a. One last property is conjugation. So if I take the complex conjugate of x of t, then I'm just going to plug it into the definition of the Laplace transform, and then note that if I factor out this conjugation operation over here, then I'm getting x of t is e to the minus s star of t. So it's just, this thing is just going to be, this inside here is x of s star. And so we get x star of s star. So this is sort of weird. You're like, okay, you put a bunch of stars in, you like sprinkled them in, and then, who cares? But it's really actually important, because if x of t is real, then x star of t is equal to x of t, and then we have that x of s is equal to x star of s star, which means that if x of s has a pole or a 0 at some s naught, then it also has one at s naught star. So all these poles that we saw that were not on the real axis, those have to appear in conjugate pairs. And so we say that the poles and zeros appear in conjugate pairs for real signals. And that's a really useful fact and important when we're trying to design filters whose impulse responses are real. So, as an exercise for yourself, try finding the following Laplace transforms using some of the transform properties here. You can find make up a couple of other functions which look, plausibly similar enough to things that you could use transforms for, and see if you can find the transforms of those signals. Getting a sense of how to use these transform properties also gives some insight into what the Laplace transform is saying about the structure of a signal. And we'll see later on how properties of a system or properties of a signal relate to the shape of the Laplace transform and the locations of the poles and the zeros.